my gosh, did you guys see the game last night?
Wait, what game? Oh no! I dropped my AirPods, phone, and claw clip into this mysterious liquid. The liquid is starting to diffuse into them. What should I do?
Oh my goodness, how are we gonna save your 3 precious objects? Which one do we save first?
Wait, I remember learning about the effective surface area on mass transfer in my mass and heat class. Mass transfer occurs when there is a concentration difference. In this case, mass transfer occurs as a liquid moves from the high concentration, which is the pond, to a low concentration, which is your fallen objects.
Okay, I kind of get it. But how do we know how fast mass is transferring into my 3 objects? And how do I know which one I should save first?
Oh, I know of an experiment we can run to simulate this scenario.
For this experiment, you will need 1.6 grams of agar-agar powder, a digital scale, a graduated cylinder, water, a microwave, an oven mitt, pH indicator such as bromothymol blue, all-purpose ammonia, a ruler, a sharp knife, a microwavable clear container, 5% acidity vinegar, a fork, and a timer. To begin the experiment, mix 1.6 grams of agar-agar powder and 205 milliliters of water in a microwave-safe container. Heat the solution in the microwave for 30 seconds, stir, and return to the microwave for another 30 seconds. Repeat this process until the mixture boils. Add a few drops of bromothymol blue until the mixture turns blue. If the mixture is green, add ammonia drop by drop until the mixture turns blue. This means that the agar is basic and we will be able to see the diffusion as it occurs. Let the agar cool until it solidifies and cut the agar into 3 shapes. A cube to represent the AirPods with dimensions of 2 by 2 by 2 centimeters, a rectangular prism to represent the phone with dimensions of 1 by 2 by 4 centimeters, and a triangular prism to represent the claw clip with dimensions of 2 by 2 by 4 centimeters. To easily compare mass changes between objects, all 3 shapes should have the same initial mass, which in this case is 7.8 grams. Fill 3 containers with enough vinegar to fully submerge the shapes. To minimize variables, the volume of the vinegar should be the same in each container. Place the agar shapes into each container, making sure that the blocks are completely submerged. Start a timer to measure the process. After 5 minutes, remove all of the different shapes from the vinegar and measure how the mass has changed. Repeat this process every 5 minutes until you reach a total experimental time of 15 minutes.
What a cool experiment. But how does this help us figure out which object to save first?
Let's walk through the math. Here's the general differential equation for mass transfer, and here are some assumptions that we can make for our process. The first is steady state, the second is no reaction, and the third is that diffusion only occurs in the z direction. With the simplifications, we now have our equation to be 0 is equal to d NaZ over dz. This means that our mass flux should be constant. We can examine this scenario more with the Fick's law.
Here is Fick's law, which models how much mass diffuses per area per time, also known as the mass flux. It models the rate at which the vinegar particles are moving through our solid agar shapes. There are 2 mechanisms of mass transfer, diffusion and convection. In this scenario, we will assume that the impact of convection is very small in comparison to diffusion, because the pond liquid isn't moving. Thus, our mass transfer is diffusion dominated.
With these simplifications, we learned that the mass flux depends on the diffusion coefficient and the mass concentration gradient, which are dependent on material properties. Since we are using the same material for each shape, we know that the mass flux for all shapes is the same, which is a constant as we learned before from the general differential equation. Also, if we define that the mass flux rate is equal to the mass transfer rate divided by the area, we can conclude that increasing the surface area also increases the mass transfer rate. Since the mass flux rate is constant, there is a linear relationship between the surface area and the mass transfer rate, which can be seen by this graph.
To measure our mass transfer rate, we recorded the mass of each shape at 5-minute intervals and calculated the overall mass increase. Graphing this mass increase versus the time, we can look at the slope to analyze the mass transfer rate. If we look at the 3 different lines, we can see that the slope of the triangular prism is greater than that of the rectangular prism, which is greater than that of the cube. This shows that as we increase the surface area, we get a greater mass transfer rate.
Oh, okay. We can say that as we increase surface area, we have a greater mass transfer in our system.
Yes, this not only applies to your fallen objects, but to real-world problems that chemical engineers are currently trying to solve, like designing drug delivery systems. Engineers need to consider how fast drugs will diffuse through tissues based on their surface area. The systems they design will need to ensure that the drugs can reach their target sites efficiently. Some other applications could be preventing the spread of pollutants through the environment or controlling the diffusion of flavors and additives in food processing.
I feel so smart now that I understand how surface area affects mass transfer rate and how chemical engineers use this kind of thinking in real world problems.
Me too. So now that we know this, we can fish out your objects, first with the claw clip since it has the largest surface area, followed by your phone, and then lastly the AirPods since it has the smallest surface area.
Oh no, they're all ruined. You guys took so long trying to explain mass transfer rate. Now I have nothing left.